This conference will now be recorded.
Okay, everybody online, I hope you can hear me. Maybe somebody can chat me a thumbs up or something if everything's working all right. You see our screen, etc. Yay, I'm getting all kinds of yeses. That's wonderful. Thank you. Okay. All right, today will be a little more rich in material compared to the last couple of lectures. Those were definitely a little lighter. We'll spend a lot of today talking about sort of the ARMA class of models broadly, and there are some subcomponents to those which you're going to learn about in great detail. By way of review, I want to start today talking a little bit about white noise and random walks. We talked a little bit about those on Thursday. And we're going to talk about autoregressive models, moving average models, and a combination of those, autoregressive moving average models. And then we'll talk a lot about using the autocorrelation function and the partial autocorrelation function, which we learned about Thursday, for model identification. Okay, so briefly with respect to review, white noise, again, remember, is discrete white noise if its values are independent, identically distributed, and we like this mean of 0. That distributional form is flexible, of course, for the W. So we saw a case where we had W that were just discrete between -1 and 1 at an expectation of 0. They had an autocorrelation function of 0 for all legs, not equal to 0. We also talked about Gaussian white noise. This was this idea that we had normally distributed values with a mean of 0 and some variance sigma squared. And then we knew that the autocovariance and the autocorrelation were going to be sigma squared and 1 respectively if the lag is 0 and it's 0 otherwise. So right, you can imagine we have just a fuzzy white noise sequence, and if we lag it and then correlate it with one another, if they're both white noise still, it shouldn't matter. There should be no correlation of white noise with white noise. Here's the time series of white noise on the left, the autocorrelation on the right. Again, right, no significant autocorrelation for lags unequal to 0. Okay, random walk was a model that we talked about briefly. We're going to spend quite a bit of time with this model in this class. Its value today was value yesterday, plus or minus some error. And then that error is white noise. And again, we don't typically we don't care what the white noise is, but we typically think about it as being Gaussian for the purposes of this. So here's a model with Gaussian white noise and a random walk. And random walks are characterized by this phenomenon where there are these deviations, which are just draws of the W, but in general, it kind of follows this path, right? You can imagine sort of this drunk person stumbling down the sidewalk. You know, they spend some time over here, and then they spend some time over there, and stuff like that, but they're kind of doing things. And random walks, because the value today is related to the value yesterday, have these strong correlations out to long lags. So they have this sort of strong long tail ACFs. We didn't talk about Thursday, but I want to mention here is something called a bias random walk, or a random walk with drift. For those of you who remember some of your genetics work, random walk with drift is something that they talk about. And the idea here is that the value today is the value yesterday plus some bias. And so it's per time step. So you could think about that as sort of an average slope in a random walk. So here's an example where on the left, we've got a biased random walk that has a bias of 1 and white noise errors with a mean of 0 and a variance of 1. And it has this very strong upward trend. And a biased random walk has an ACF a lot like a regular random walk. The bias doesn't really affect that. That's just a constant there. So anyway, it has high autocorrelation out to long lags. We talked about differencing on Thursday. And if you difference a biased random walk, what you get is essentially a constant mean, or a level, we say in time series, plus white noise. So Here on the top is our biased random walk model. You take the first difference of that, right, which says you subtract the value next to it, so x of t minus x of t sub 1, so we take that from both sides. That term zeroes out, and on the bottom you're left with the first difference is going to equal that bias plus white noise. Okay, so here is the first differenced biased random walk on the left there, so it just looks like white noise setting around a mean of 1. Yes, Mark?
What happens if you difference a unbiased random walk?
That's a great question. So let's go back here. Does this model right here, what would happen if we difference this? So, yep, that's exactly right, Because if we took the first difference, that just means subtract x of t minus 1 from both sides. So this would zero out, we get white noise, and the first difference would be white noise. So that's exactly right. Okay. All right, so the remainder of today, we're going to talk a lot about so-called linear stationary models. So we talked on Thursday a lot about stationarity and what it means for a time series to be stationary. One of those we talked about last week as a linear filter was this idea that we could sort of smooth a time series out by substituting the observed value today by some sort of average of those values on either side of it. We're going to extend those ideas to this sort of general class of autoregressive moving average, or ARMA models, as they're called. So first of all, we're going to talk about autoregressive models, or AR, as they're referred to, are widely used in ecology to represent sort of the current state of nature as a function of its past state. So we'll see later in the quarter that you can represent density-dependent population growth using a very simple discrete time series model. You could add in covariates and make things a function of the environment. You can have time series interacting with one another. So anyway, autoregressive models are widely used in sort of in ecology general, where fisheries I lump in there as well. Autoregressive model of order P, or ARP as we call them, is defined as x of t equals b1 times x of t minus 1 plus b2 times x of t minus 2, etc., out to whatever lag p we've chosen. Right, so if it was just lag 1, everything else would go away and you have this white noise term. And the important part here is number 2 on this list, that for lag p, phi can't be 0. Because that just means that you don't need that term. So really your model is lag p minus 1 if you have a phi of p0, right? So this is an autoregressive model. Here's some examples of autoregressive models. An AR1 model on the left. The middle one is an AR1 where phi equals 1, and that's a random walk. Right? So a random walk is an autoregressive model. There's an AR2 model. So you have some today's value is a function of yesterday's plus a function of 2 days ago, that sort of thing, plus error. Here's some plots of different AR models. If you just look at these, there aren't really qualitatively any particular differences among them, and that's often the case with autoregressive models, with the exception of one particular case that I'll mention in a moment. But anyway, if you look at these in general, I think you can convince yourself that the values would seem to be related from one time step to another. They don't appear to be white noise or something like that. Okay, so in particular, we're going to focus a lot on stationary ARP models. And remember that in order for a time series to be stationary, it really needs to have 3 things. It shouldn't have any change in the mean or the variance, so we don't want any sort of step changes as we move through time. We don't want to see a time series that sort of explodes, like a sequence of random walks would do, that sort of thing. We don't want any particular increase or decrease, and we don't want to see any of this seasonal patterns, these sort of regular cycles, or whatever shape they may be, but sort of this repeating sequence related to that. Well, we mentioned the other day that if we just want to use our eyeballs to identify stationary models, that really doesn't work very well. That's pretty convincing. We were all pretty bad at it. So we're going to seek here a formal means for doing that. So a way to actually know whether the models we're dealing with are in fact stationary or not. One of the best ways to do that for small order autoregressive models, so where P is relatively small, is to write out the model using this backshift operator that we introduced last time. So we have an AR P model up above. We think about rewriting this in terms of a backshift operator. So everywhere there's an x of t minus 1, we have a b. If it's t minus 2, that's b squared. If it's t minus p, that's b to the p, right? So, and we can write that model out shorthand by using just phi sub p with a backshift t. So that means all of this b sub p of b. That's just a shorthand way of writing that out. If we treat b in that equation as a number or a set of numbers, we can write out this so-called characteristic equation. So we take this b of b and we set that equal to 0 and we solve for the b. And in order for an AR model to be stationary, all roots of that equation must exceed 1 in absolute value. Well, what does that mean? Okay, so I think it's best demonstrated with an example. So let's think about that AR1 model I mentioned just a little while ago. So x of t is equal to 1/2 of x of t minus 1 plus some white noise. So if we rearrange those terms, we just bring the x's to the left side and write that in the backshift notation, we'd have 1 minus 1/2 b times x equals wt. If we now write out our characteristic equation, we pull this bit inside the parentheses out, we set that equal to 0, we can see in this case that b equals 2, and therefore this model is in fact stationary because b is greater than 1. So that AR1 model is stationary. How about this AR2 model that I showed you earlier? Okay, you do the same thing. You write this out using the backshift notation, so you have to collect all the x's together on the left-hand side. Write that out using the backshift notation. Write out your characteristic equation. In this case, it's a polynomial, so there are going to be 2 roots. And so you have to remember the quadratic formula, right? Minus b plus or minus a square root of, etc. So if you do that, one of the b's is about minus 1.35, and the other one's 1.85. So that model is not stationary because one of those roots is not greater than 1. So it's not good enough that one of the roots is, all of the roots have to exceed 1. Okay, how about a random walk model? I sort of preempted this earlier by telling you that random walks were not stationary. Well, same thing. You write that out using the backshift operator and set that equation up, and it's pretty easy to show that b equals 1, which is not greater than 1. So no, random walks are not stationary. It turns out that for the case of AR1 models now, just AR1, not 2 or more, we can define a space over all of those are going to be stationary. And this will become important as we move forward in the class. So first, think about the case where phi is positive. So we have a positive phi here. So we have our AR1 model is going to be x of t equals phi times x of t minus 1 plus w. We write that out using a backshift operator and set that equal to 0. We solve and we see that b is going to be equal to 1 over phi, and if we require that to be greater than 1, that implies then that phi is going to have to be between 0 and 1, that open interval. Cannot be 0 because then b is going to be infinite, and if it's 0, it's not an AR1 model, right? Because that means phi is going to be 0. So cannot have that. If it's 1, then that b is going to be equal to 1. It's going to be a random walk. Okay, so that's the case where phi is positive. What about the case where phi is negative? We do the exact same thing, right? We set this up as before. We write it out using the backshift notation, set that equal to 0, do the math, and here we find that phi is going to have to be on the open interval -1 to 0. So that means we can say that AR1 models are stationary if and only if the absolute value of phi is less than 1. And I should subscript this and not equal to 0, because then it's not an AR1 model anymore. Okay, so again, this will come into play later on in the quarters and move forward. Okay, let's think about some AR1 models as well. Here's a case where I've simulated 2 different AR1 processes. Both are stationary. Both have the same magnitude sign or value for phi. One's positive and one's negative. So the one on the left is positive 0.7 and on the right it's minus 0.7. And the thing that's particularly characteristic about this is for AR1 models, well, not just AR1, higher order as well, if phi1 is negative, it will do this sort of 2-point oscillation. So if you think back to a couple lectures ago when I just showed some examples of time series and there was one that did this and then it damped out for a little while and this kind of funny thing, that was just a case where I had a negative X or sign on the phi1 component. So there's 2 different ones. Okay, here's a case where they're both positive, but they have very different magnitudes. So the one on the left is 0.9, the one on the right is 0.1. I plotted them on the same scale. So you can see that the one on the left, as phi approaches 1, it's going to become a random walk, right? So right now it's still stationary, that phi is less than 1 in absolute value, but it's kind of spending some time away from the mean of 0, right? It gets off in these kind of areas and it spins around. Contrasted with the one on the right where phi is getting down pretty close to 0. So as a phi approaches 0, it's just white noise. So the one on the right is looking a lot more like white noise than the one on the left. Okay, let's think back to this autocorrelation function that we mentioned. It's the correlation between a time series x of t and just a time shifted version of itself. So we take a time series, we replicate it, we shift it over, and then we ask for the correlation between the 2. And here's some ACF now for that first model I showed you, or the first comparison rather, where there was same magnitude phi but different signs. And phi is relatively large here, so the autocorrelation function is significant out to several lags, but you can see that the ACF oscillates for the one where phi is -1, right? It goes positive, negative, positive, negative, positive, negative, which makes sense because as soon as you shift the thing, it's going to be completely out of phase with itself, and then you shift it again and be back in phase, right? So those are just, again, diagnostics helping you moving forward. Here's the ACF for those cases where they're both positive, but they have very different magnitudes, right? The one on the top that's fairly close to a random walk has this long tail on the ACF, whereas in this case, the one on the lower panel, the 0.1, has a significant lag, or a significant autocorrelation at lag 1, and it's 0 anywhere else. So you can really think about in sort of a context, and I'm kind of preempting the future a little bit. If you've had ordinary differential equations classes, or you've done applied math where you've tried to solve these things and you've thought about eigenvectors and eigenvalues, in a univariate space, this AR1 coefficient is sort of akin to that eigenvalue. So it's sort of the dampening coefficient, right? So you think about this ACF on the upper right, the phi is relatively large, so it has very low damping. It's going to take a long time for that ACF to go to 0. The one on the right, it's very small, so it goes, hits 0 very quickly, so it's damped out. Anyway, there'll be more about that later. Okay, that was autocorrelation function, remember? And we also had this partial autocorrelation function. This was the idea where we wanted to remove all that intermediate correlation between 2 points, because, right, if these 2 are correlated and these 2 are correlated, then these, whoops, sorry. Okay, these 2 are correlated. For those of you online, I just flipped everyone off. So the idea was you remove this intermediate correlation and then just look to see what's left over between the two values. Okay, so here's the two models where phi was 0.7 and minus 0.7. And, but I've added a couple more terms. So these are AR3 now. And the AR3 terms are the same except for the one on the top that's negative. So the time series on the left-hand column look quite different to one another. And you can see the effect of that on the ACF in the middle column. The upper one has this kind of long dampening tail, and the other one has a long tail, but it oscillates back and forth. If you look at the PACF now, you see that once we remove all that intermediate correlation, in particular, it goes away. So right now, there's only significant partial autocorrelation at lags 1, 2, and 3. And everywhere else, it looks to be 0. So now I'm showing you plots of the partial autocorrelation function for AR models, ARP models that go from 1, 2, 3, and 4. And I'm wondering if anybody can spot the relationship here between the order P and the lag K.
Yeah, you've got significant autocorrelation out to the order of the AR.
That's exactly right. So for ARP models, you will have significant autocorrelation up to lag P and 0 everywhere else. So now you have a pretty good diagnostic if you're starting to think about these things. If you have an ARP model and you look at the ACF, it's going to tail off relatively slowly depending on the number of lags and the value thereof. More definitively, however, is going to be that partial autocorrelation function, because it's going to tell you that after lag P, it should be 0. So there's a good indication if you're looking at the two diagnostics for a time series, the ACF and the PACF. If you see the PACF just cut off after a particular lag, it's a pretty good idea that it's ARP. It's not foolproof, but it's pretty good guidance. Okay, how about moving average models? We're not going to talk a lot about moving average models in this class. In general, moving average models are used for forecasting, particularly in finance. The forecast models that we use usually involve some sort of more predictive context where you're using something like a covariate X temperature to predict catch or something like that. These models are used where there's some measured deviations in a, say, index and a realization, an individual stock relative to that index, and using those past deviations, you can make a pretty good prediction about what's going to happen. So that's what they're most commonly used for that I'm aware of. A moving average model of order Q, or we say MAQ, is defined as such. Today's value, X of t, is going to equal some error term, WT, plus some basically weighted sum of all the other error terms in Q past. So we typically think of these having where W is white noise. It could be Gaussian, wouldn't have to be. Most of the models we deal with, it will be. And so each of those XT is really a sum, some weighted sum of just the recent deviations. Because of that, all moving average processes are stationary because they are finite sums of stationary white noise processes, right? So because all of the WT terms are white noise, if you multiply those by a scalar, it's still going to be white noise. You're just affecting the variance. So regardless of what moving average model you're dealing with, it is stationary, assuming it meets the criteria that the W are white noise. So here's some examples of moving average models. Again, qualitatively, there's not a lot of difference among those different orders between MA1, 2, 3, and 4, where the signs are varying not a lot, as it turns out. Here's a couple of MA models where on the one left I've got an MA1 and on the right I've got an MA2, and all I did was move the sign or add another one. So the first one, it's WT plus 0.7, WT minus 1. And on the right, it's now the 0.7 times WT minus 2, and it's minus 1 times T minus 1. And here you can see it's had a pretty big effect on the behavior of those time series. One is doing much more of this oscillatory pattern that we've seen before, and it looks much more like white noise. The other one actually appears to be a little bit more like a random walk. So you can make qualitatively very different models without much structural difference to the underlying models. It is possible to write ARP models as an infinite order moving average model. And this is a little more than just a gee whiz fact. It's a little bit of something we kind of need in order to solve some of the models using whether it's software or just theoretically. So bear with me here. So for example, consider an AR1 model. So we just have one phi, x of t equals phi times x of t minus 1 plus a white noise term. If you think about this, we could replace x at t minus 1 with its value phi of xt minus 2 plus xt minus 1, right? And just do this recursively. So at some point, we'd get to this point where we would have x of t equals wt, and then this long sequence of wt's where we had phi, then phi squared, then phi cubed, up to phi k, etc. And then we end up, why did I, it's a typo here. To check that. Okay. Yes, no, that's correct. Okay, so if our AR1 model is stationary, then we know that the absolute value of phi has to be less than 1. And that would suggest then that the limit as k goes to infinity, right? So we're talking about an infinite order MA model here. So k is going to be infinity. A real value less than 1, an absolute value raised to an enormous power, is essentially 0. So that means that in our moving average model here, this last term, this last x of t minus k minus 1 term drops out, and you're left with x of t purely as a function of past errors. So this is a moving average model now for an AR process. Okay. The converse is also true, and this is the trick that we need to help us with sort of these solutions. An MAQ process is going to be invertible if it can be written as a stationary autoregressive process of infinite order but without an error term. So what do I mean by that? That means we're going to have WT as a function of only x's, right? Just like before we had x as only a function of w's. So think about an MA1 model here. So the first thing, we write that out, x of t equals WT plus theta times WT minus 1. And then the first thing we do is just rearrange terms. So we just move the x's or we just switch that around rather, sorry. And then we can do the same trick we had before. If we just start doing this recursive substitution where we take w at t minus 1 and we replace that with x t minus 1 minus theta wt minus 2, etc., we'll get the exact same thing where we can get this out and we'll just end up with this large sum where the wt is going to be x of t minus all these fractional values of the past x of t's. Ultimately, though, we're going to end up with some error term. So the last little bit is going to be minus theta raised to an enormous power times some small error term.
I got a question.
Yep.
Why can't we just change the theta wt minus 1 to theta times x t minus 1? You did it in the slide before too, but like how are you just converting from, there might be a typo there, but when you multiply the theta and times x of t minus 1 minus theta, what is now wt minus 2, why can you do that?
Well, that's exactly the definition of this value. So think about starting with this, this equation right here.
Oh, I see.
If this were WT minus 1, then this would be WT minus 2.
Right.
So anywhere we
Just
have
rewrite.
WT minus 1, we just take exit, well, this would be minus 1, the minus 2, right? We pull that out and stick that in.
Okay.
And then we want to know, okay, well then what's WT minus 2? And so we did, this would be T minus 2, T minus 2, T minus 3, right? And then we'd stick that. And we could just keep doing that infinitely. And then you'd end up with something that more or less looks like this, where if you did it K times, this is what you get. So there's still this error term out here. We're trying to get rid of this error term. We want it, the WT to be purely an autoregressive function, no error term in it. Well, again, if we think about constraining these thetas, the absolute value of theta to less than 1, then the limit of minus theta k plus 1 times this normally distributed, or I'm sorry, a white noise term, as k goes to infinity is again going to be 0. So this last error term will drop out because that just goes to 0. And this just becomes a large sum with x of t plus the sum of infinity of all of those past values. And if you think about this model for a moment, thinking about having these constraining these thetas to be less than 1 in a moving average model actually makes quite a bit of sense, because think about, I'm going to back up here, slide. Why did I, oh, so here, if x of t is going to be an error today plus some value of an error 2 days, yesterday, and some value 2 days ago, if the thetas are greater than 1, that means that, in effect, a long time ago, as we move forward, these are going to be their power functions, right? So you're going to have values in the past are going to be way more influential than values in the most recent past. And especially in a forecasting context, that doesn't really make much sense, because there's usually a lot more information, especially in financial markets and those sort of things, and what happened yesterday or the day before that than in what happened months and years ago. So in general, there is a desire to constrain those values to be less than 1 in absolute value. It also turns out you can make the model invertible if you do so. Well, who cares if we can write a model out and make it invertible? Well, it turns out that when we actually want to solve for the parameters in these models, we have to have a means for doing that. And if we don't make it invertible, then we end up in a bit of a conundrum, because here's a case where we have an MA1 model that would be equivalent if we had no information about the variance of the WTs. So if we estimated the autocorrelation function of these, the mean of these, the autocovariance function of these, they would both be the same. And so basically what happens is the upper model I have 1 over some value, and in the lower one I have the value. So it's just a reciprocal, and then the variance here has been multiplied by that sort of reciprocal square. Right, so the variance of the top equation is going to be 25 plus 1/25 of 25. That's going to be 26. And this one down here, the variance of this one is 1. And the variance of this one is going to be 5. So that's 5 squared, 25 times 1. So that's 1 plus 26. The variance of both of those is 26. And I don't think I included a plot here. I should have done that. But if we computed the ACF of those, it would be the same. So usually what we do is decide we're going to insist that the model is invertible, which means we would choose the upper solution here. So we're going to make the thetas less than 1 in absolute value. Okay, just as we talked about for autoregressive models, the ACF and the PACF are going to be useful to us here. So here's an MA1 model and an MA3 model, where I've got the ACF in the middle column and the PACF on the right-hand side. And it looks like for the upper one, maybe there's significant autocorrelation at lags 1, nowhere else. The lower one, maybe it lags 1, 2, not 3, maybe 4. And maybe there's partial autocorrelation at lags like 1 or 2, but we're not sure. Just like we did for the AR models, here's the ACF for MAQ models. So here's orders 1 through 4. And can anyone spot the? You know, come on.
It's the same again.
It's right, yeah. So this time it's the ACF that's telling us something about the order of a moving average model. So in the upper right, there's significant autocorrelation at lag 0 because that's it with itself. It's perfectly correlated. It's 1. And then you see it at lag 1, and then it's at lags 1 and 2, lags 1, 2, and 3, lags 1, 2, 3, and 4. This one, it looks like perhaps that's not, but that's only because I simulated these. But again, you can show via actual algebra that this is in fact the case. So building on our table, if you have an MAQ model, the ACF is going to cut off after lag Q. And the PACF is going to tail off typically slowly and with no particular regular pattern. So by looking at the ACF and the PACF of a time series that's stationary now, right? You've gotten rid of the trend and you've gotten rid of some seasonal component. You think you've got something that's stationary. If you see the PACF cutting off, it's probably an AR model. And if you see the ACF cutting off, it's probably an MA model. Okay. Let's combine those two now to talk about autoregressive moving average, or ARMA, PQ models. So you'd write those very simply just by combining the two things we had before. So we have the X is going to be some function P fees in the past, plus some white noise term, WT, plus some fraction of past WTs. And the order P gives the number of AR coefficients, and the constant Q gives the number of MA coefficients. So we're just combining those two terms. You can write out an ARMA model using the backshift operator, just like we did for AR and MA models. ARMA models are going to be stationary if all of those roots are greater than 1, just like it was for AR models. And they're going to be invertible if all of those roots are greater than 1. And I'm not going to bother with the algebra here. You can look it up if you want, but it works the exact same way that we showed before. Here's some examples of ARMA PQ models. The upper left is an ARMA 3.1. The lower left is an ARMA 1.3. The right-hand side are both ARMA 2.2s. And you can see that, yeah, qualitatively, sure, there's some differences there, but you know, how would you really know? Well, again, you'd have to start to do some more diagnostic measures to look. Here's the ACF for those same 4 models. So you can see again in the upper right, that first AR coefficient is negative. So the ACF does this oscillation. It bounces back and forth. So that's a really good indication that you've got that. In the others, you could tell that the ACF is just sort of slowly tailing off because all of them have at least an order 1 autoregressive process with a relatively large coefficient. So you should expect that. Here's the PACF for those models. There's no particular strong pattern here. And that gets to be a bit of the rub when it comes to ARMA models, because for both the ACF and the PACF, yeah, they kind of tail off without a whole lot of things. On Thursday, Eli's going to talk a little bit more about model identification and some of these things for ARMA models. So there are some better ways to go about this. And you're going to see in lab that there's actually some great R functions that will just search over space and figure out which of these would be best for you based on some criteria that you establish. So anyway, it's not an exact science, but particularly if you're trying to separate AR versus MA models, looking at the ACF and the PACF are going to be really valuable tools. Just toward the end here, I want to spend just a few minutes talking about non-stationary models. we've been talking about stationary models. And one of the most kind of popular out there are what are called autoregressive integrated moving average models, or ARIMA. And basically, they use an index system where you have P, D, Q. The P is the order of AR, the Q is the order of MA, and then you have this D, which is the order of differencing. So the way an ARIMA model works is there's some differencing that goes on in the background before the estimates of P and Q are made. So for some differencing operator, or some difference, I should say, D, where D is going to be greater than 0, a time series X of T is going to be an ARIMA PDQ process if 1 minus the backshift raised to the dxt is an ARMA process. Okay, this is best illustrated with a simple example. Let's say X of T is an ARIMA 110. So that means it has an AR component of 1, it has a first difference, and it has 0 MAs. Then the difference of X of T should be an ARMA 10 process, right? Because there's this, we see the order of differencing here is 1. And so that's what's going on up here. If we back this out, so you could, if your data were following an ARIMA 110 and you fit that using auto function and said, yes, look for orders of D1 or greater, it would figure out that it was an ARIMA 110. If you first, before handing the data to the function, you first differenced them yourself, and then you handed it to the search algorithm and you said, yeah, look for an ARMA 10 model, it would find that, and they would be exactly the same. So for example, here's some simulated data in the upper left, an ARIMA 110, and there's the ACF on the right, and here is an ARMA 10 model on the first differenced data and the ACF. And it turns out that the parameters that you estimate from this model are exactly the same. The AR1 coefficient would be identical. Okay, so just to wrap up here with respect to review, so we talked again about white noise and random walks. We're going to talk a lot, well, not specifically, but those will be something that will keep popping up all the time. Probably every lecture from now on, you're going to hear something about white noise and random walks. We talked a lot about autoregressive models, and you're going to hear a lot more about those moving forward too, because as I mentioned, autoregressive models are very important in general in ecology, and a lot of other fields as well, but we can do a lot of things with them in fisheries and ecology. We talked about moving average models. Again, those are generally sort of used in finance. We're not going to focus heavily on those here. And the combination of those two, Eli's going to talk more about that on Thursday. And then lastly, we spent quite a bit of time looking at ACFs and PACFs for those different AR and MA processes and seeing how those can be useful for one another. Okay, so with that, I am going to pause and, excuse me.